In this video, we're going to talk about enzyme substrate reactions and Michaelis-Menten kinetics, which are a really nice application of Hill functions. So for a little bit of context first, let's talk about how enzyme substrate reactions actually take place. So this is the general cycle of the reaction. It starts off with an enzyme with an active site available, and a substrate that binds to the active site gets converted into products and leaves the active site already as a product of as two products, in this case glucose and fructose. So there are a couple of intuitive things about the process that one can notice right away. First of all, if we have a certain number of enzymes available, if we increase the substrate concentration, then of course the reaction time is going to get faster because active sites are not going to sit idle for long. If there's a lot of substrate that can bind immediately as an active site gets freed up, then the reaction time is going to be faster. On the other hand, it's also pretty clear that after a certain point, if the concentration of the substrate is already really high, this is not going to speed up the reaction because there's going to be simply no active sites available for the reaction to take place any faster. Another observation here is that if there's no substrate at all, there's no reaction happening whatsoever. So the two of the main observations that we just made are actually what is a basis for Michaelis-Menten kinetics in describing the enzyme substrate reaction time. No substrate present means the speed of reaction is zero, and at high concentrations we reach some sort of maximal level of the speed for the reaction, some kind of a plateau. And that immediately kind of gives us some idea that Hill functions are probably a good descriptor for that. And in fact, that's true. Michaelis-Menten kinetics is just one particular type of a Hill function. This is what we will call a linear Hill function because the powers of x on top and bottom are 1. Michaelis-Menten kinetics are named after two people, Leonard Michaelis and Maud Menten. Leonard Michaelis is actually primarily known for this work, and Maud Menten has done a bunch of other things in terms of medical research and has some really close connections to Canada and to Fraser Valley in particular. She was one of the first women in Canada to obtain a medical degree and then subsequently a PhD. She actually had to leave Canada for both because at the time there were very limited options for women in Canada at all, and she could not have obtained her PhD from Canada. She, during her studies, decided to travel to Berlin to work with Menten in his lab, where they've done work on enzyme kinetics, and then came back to US to work at a number of institutions, and eventually ended up in British Columbia, where she actually continued her academic career. The one interesting connection to Fraser Valley that she has is Menten spoke a number of languages, one of which was Halkomelem, that she learned in school because some of her indigenous schoolmates, that was their native language. And of course, Halkomelem is the native language of the Stolo people out in the Fraser Valley. I encourage you to read more about both Maud Menten and Leonard Michaelis. They both had a really interesting biography, and it just gives you a little glimpse into the history of biology and mathematics at the same time. Let's take a closer look at this function and see if we can apply some of our analysis from before to sketch it or to give us some idea of what a graph might look like. I'm going to go over this fairly quickly. You'll see a little bit more in class, right? So once again, the same way we analyzed Hill functions before, we'll analyze the Michaelis-Menten kinetics function. So for small values of x, the function will actually resemble a over bx, which of course is a straight line with slope a over b. Remember that a and b are both constants. For large values of x, what we have is that it will resemble ax over x, which is, just a. So it will plateau out at some maximal reaction level. So to sketch this out, what do we have? Again, we're only going to sketch it for positive values of x because the reaction is only positive for is only possible for positive concentrations of a substrate. There's no such thing as negative concentration of an element. So these are my x values, which are the concentration. So what we have is that near the origin, for small values of x, my function looks like a line with slope a over b. And for large values of x, my function looks like a, some horizontal asymptote at a. So maybe let me label off a. And here we're starting off as a line and then eventually flattening out. The one interesting thing about this function to note too, that supports intuitively why it can be used for description of enzyme kinetics, is to note that at small concentration, so somewhere here, if I make a small jump in concentration, the reaction time will increase quite a bit. But if the concentration is already large and I increase it further, the actual change in reaction time is essentially negligible. And that makes sense. If I have just a little bit of substrate and I say double the concentration, then the reaction time will get faster because active sites will be working and not sit idle. But if the concentration is already so high that the active sites are primarily occupied at any given point in time, then increasing their actual substrate concentration will not really affect the overall reaction time.